All right, so Unit 3, this is going to be our probability unit. So it's stuff that will kind of come back throughout the year, but it's kind of its own distinct unit. Typically in college, again, it's the third unit they do too. So that's just kind of why I placed it, just so we can get into probability before we go into all the various other types of probability. So this is going to be what's known as basic probability in the sense that we don't need any type of specific formulas or any type of distribution to do it. It's just kind of based off of each of these problems. So, overview of the unit. This unit will cover all the probability analysis and calculations that we'll need for the remainder of this course, meaning any type of probability we cover in here might come back at some problem later on. Again, singular or simple events. So the word simple in statistics and probability does not mean like it's less challenging or it's easy. It just means a singular or like a one-time thing, meaning there's only one event that's occurring. So we're flipping a coin or rolling a dice or pulling a card from a deck. There's not more than one thing going on. This will help us build into what's known as a compound event, so meaning more than one occurrence. We'll talk later on about conditional probability, so kind of like the chances of something happening given this already happened. So like we'll calculate from your guys' grades probably later on. The chances that given you studied, what's the chances you passed a test, right? So that's something, again, fairly useful and worth knowing. We'll talk about permutations and combinations. That's just a way of determining how many possible things can occur. So that gets more into like playing cards, figuring out the likelihood of a given hand occurring, locker combinations, determining passwords type thing. Okay, so why do we need to study probability? So we encounter statements given in terms of probability all the time. This is probably the most common math thing that you're going to come across in life is hearing about odds or likelihood. You're definitely going to see these probability statements much more often than you will, say an algebra 1 equation or see a triangle with the hypotenuse labeled in life. So we come across things like an excited sports announcer claims that Sheila has a 90% chance of breaking the world record in a certain event. A true-false question, the chances that you guess right is 1/2. Let's see, the Right to Health lobby claims that the probability is 0.4 of getting an erroneous report from a medical laboratory at a low-cost health center. So again, basically this is a nice little textbook example here of the variety of ways we see statistics or probabilities given to us. So we can be given things as a percentage, like we talked about in the last unit, so going between decimals and percentages. We can be given that decimal, or that's a formal probability. So a probability is a number between 0 and 1. We can express them as a percentage or as a fraction. So all of those things at this point, you need to be able to do interchangeably. So if I ask you to give me something as a fraction, you already should know how to do that. To give me a probability, that's just a typical decimal, or as a percentage. So again, that's kind of the make sure you read the directions right type deal, which again, we'll model those different strategies on how to convert to them, how to use technology and leverage that to avoid any challenges we might have with fractions, so on and so forth. Key idea on this slide is when we use probability in a statement, we're using a number between 0 and 1 to indicate the likelihood of an event. So at any point in time, if you're doing a probability question, your answer is a negative number or bigger than 1, you know you did something wrong. So again, every single answer, pretty much for the rest of the year, anytime I ask you what's the chances, the area under the curve, the probability, the likelihood, pretty much every answer in stats is between 0 and 1. Later on in the year, we'll get answers that aren't, but that's also not probability. So rule of thumb, the next 3 units, pretty much every answer is between 0 and 1. Also, please don't think that's going to mean you have a really good shot at guessing, because there's, as we know, infinite amounts of numbers between 0 and 1, because everything's going to be a decimal. Alright, so starting off with the basics here. Probability is a numerical measure between 0 and 1. I'm going to keep saying that, because then there's no way we're going to forget it. That describes the likelihood that an event will occur. Probabilities closer to 1 indicate that an event is more likely to occur. Closer to 0 means less likely. So that's kind of intuitive. That's because 1 stands for 100%. So if there's a 100% chance of something happening, that means it's guaranteed to happen. That's why I said, what is the probability that you're all in school right now? You are all literally here right now, so the probability of that is 1. Right? So if something is guaranteed to happen, like you're going to breathe oxygen today, that probability is 1. In practice, there is very few things that are guaranteed to happen outside of your basic bodily needs to survive that day. Like, drinking coffee. Maybe some of you usually drink coffee, but you're not guaranteed to. Maybe you wake up late. Same thing with the idea of 0, meaning it is never going to happen. So, like, I am never going to sprout wings and fly away. Like, that's literally just not going to happen. So that would be a probability of 0. But if I said something like, oh, what's the chances that I win the lottery today? It's pretty darn close to 0, but it could happen. So we'll talk about the idea of like a true 0 versus a theoretically not very likely. All right, a little bit on notation. So right here, P parenthesis A parenthesis. That's read as P of A, or the probability of A happening. So anytime we see the letter P, that kind of stands for just probability. So this is the probability of whatever A is. You'll see in most cases, I just write out a description here. So it's not as formal as you'll see in probably a college class. But I feel like when you write out the descriptions of what it is the events or event is, it'll be more helpful. So again, the way I write probability will probably be a little different from what you'll see in college. It's a little less formal, but hopefully helps you understand it better. And again, it's equal to 1 if we know it's going to occur, and 0 if it can't. So just kind of getting those ideas hard in our head there. Those we won't see a whole lot of, as we've already talked about. So the big one is just knowing how to read it. All right, just some more little introductory vocab. There is no portion of this exam that's going to be like, write these definitions out. It's more so just helping you understand. So this isn't something totally worth writing down, just kind of getting an idea. So a statistical experiment or observation can be thought of as any random activity that results in a definite outcome. So what that means is that there's no if, ands, maybe, or buts when we do statistics and we do probability. It's discrete and it's definite, meaning that there is one thing that ended the outcome. So if I flip a coin, statistically, a coin is literally never going to land on its side. So we don't consider that. Now, I know what you're saying, like, yeah, I've seen it in a video. But, like, again, like the probability of that happening is so freakishly low, we don't consider it. So when we flip a coin, it is either heads or tails. Like, that's it. When I pull cards out of a deck, there's a set number of things that can happen. It's not like you're wow, I'm surprised. Like, you know kind of what's coming there. You're going to grab a card, you roll a dice. It is not going to balance on a corner. You're going to get the numbers 1 through 6. Like, one of those is going to occur. So a definite outcome just means like there's no debate as to what the end was. So it's not subjective, it's very objective, just like all of, well, mathematics. Okay, an event is a collection of one or more outcomes of a statistical experiment or observation. So an event, again, it's what happens at the end. So a simple event means that we're just talking about doing one thing and seeing what happens. So rolling a dice is a simple event. Which is also the next vocab word. That was really convenient. So again, simple event means we happen, or one thing is being measured, or one thing is being observed. A compound event is when we do more than one thing. So maybe I roll a dice, and then I roll another dice. Or maybe I flip a coin, and then I roll a dice. Or maybe I pull a card, and then pull like a bingo ball out of one of those giant bingo things. So again, if it's more than one event, it's compound. If you're only doing one thing, it's simple. And then the set of all events is what's known as a sample space. So those are not necessarily hard to derive, but again, we'll do some practice with them just to get them down, as well as kind of talk about like the big one we'll use a lot. Okay, do not write any of this down. This is just one of those things I kind of have to put in here because, did I spell technical right? I did. Fantastic. Well, because it's in most textbooks, and I want you guys to at least get a bit of experience seeing how textbooks write things, and can sometimes overcomplicate them. So we have a probability assignment based on intuition, incorporates past experience, judgment, or opinion of estimating the likelihood of an event. We don't really use those except with really obvious things. So if I asked you, what's the probability of getting heads, what is it? Yep. What do we got? Yeah, 50%, right? Heads. It's one of two outcomes. So intuition, essentially we only use that when there's like It's something you all should know. How many cards are there in a deck? 52, 54 if you count the jokers. In typical standard decks, we take the jokers out. We'll get to that. I'm pretty sure I have a picture of a deck of cards in here, so we can memorize those real quick. But again, that's the key idea here, is that intuition is like, it's not something you'd ever actually really justify any statistical conclusion on. So basic intuition is like knowing what the outcomes are of flipping a coin or how many sides are on a die, like not terribly challenging stuff. All right, this is a big one we're going to work with, is relative frequency. So figuring out how much it actually happened. So this looks really complicated, right? It says probability of event equals relative frequency equals F over N. F is the frequency of the event occurrence in a sample of N observations. That's like saying if I flipped a coin 50 times, count how many heads there are, right? So if I wanted to find out a sample probability here, it just means take the number of yeses divided by the total. So if I said, how many of you drove to school today? Raise your hands. All right, so I see like 6 of us, and they say there's 30 in the room. So the probability of someone in this room driving to school today would be 6 out of 30. We'll talk more about these later on. So again, just kind of getting used to seeing the formula. So again, that's what this is here at the bottom. So what this is here at the bottom is just kind of that in words. So the number of outcomes favorable to events, the total number of outcomes. So favorable is totally a subjective term. It just means like what we're looking for. Favorable might be passing a test. Favorable might be students who got a C on a test. Favorable might be students who showed up to take a test. It does not matter. It's literally just subjective to the problem. So there's no connotation of positive or negative outcome with that word. All right. First one. So staying with our simple, basic, get the gist down thing. So we have, let me go ahead and throw this on a typable document. Hang on, I think I had a blank Word document here we could use. Alright, there we go. Okay, so we have a random sample of 500 students at Joliet Central were surveyed, and it was determined that 357 wear corrective lenses, something in contacts or glasses. For our first one here, we want to estimate the probability, so I'm just going to call that part A. Estimate the probability that a student selected at random wears them. You're going to hear a lot of words like that, selected at random, which we should be used to by this point. It just is like the statistical wording to basically say like, it's a fair random pick. So, what I want to find is the probability wears corrective lenses. Now, again, one of the biggest mistakes that students over the year have made is when we start with the really easy stuff, they don't get used to writing these things out. And then when it comes to the more complicated stuff, they have no idea how to write them out. And it's like starting back at square one. So as annoying as it is right now, because some of you probably already did this one and are like, wow, this is super easy. Why is he writing out what we're finding? It's blatantly obvious. Trust me, if you get used to writing things out, it helps. So instead of writing like probability of A, I just put literally what I'm finding. The probability that they wear corrective lenses. So how many students wear corrective lenses? 375, right? How many total students are there? 500. I'm just getting a calculator. I really don't feel like doing that one in my head. All right, so 375 divided by 500, 0.75. So for practical matters, like when I made the answer key, I just left everything as a fraction because that way you could see the quote-unquote work that I'm doing. On the test, a lot of it's multiple choice, so you have to be able to get to anything. So be able to reduce a fraction. So let's say I wanted to reduce a fraction here. Maybe I wanted the answer to be 3/4. So whatever calculator you're using, whether, again, I'll show you how to do that in GeoGebra in a bit here. But again, know how to reduce a fraction, know how to find a decimal, and know how to go to a percent. But again, those are things we already should know at this point. Okay, the next thing we're going to talk about here in part B is going to be the complement. Oh, go away. Sorry about that, guys. Why keep doing that? There. Okay. So the complement, it means the opposite. So the probability of A complement is 1 minus the probability. So what this basically gets down to is that it's the probability of something not happening, right? So the complement means not happening. So complement means not whatever that event is. So in this case, we have the event, the probability of Ware's corrective lenses, right? So what I'm finding with the complement is the probability that they don't wear And now the rule is defined as, because again, now if I say the probability of heads, that's 50%. The probability of tails is 50%. When you have all possible outcomes considered, so the probability of something happening or not happening, those two things always need to sum up to 1. So when we're thinking about wearing corrective lenses, it's a binary outcome. You either wear them or you do not. So if the probability that I do wear them is 0.75, then the probability that I don't would be 1 minus 0.75, or 0.25. Using the complement is not something that's 100% necessary. It's just a really convenient way to shortcut a lot of problems. So again, when you see me utilize the complement, just know that you technically don't have to. If you get to the same answer at the end, it's totally cool. It's just going to save a lot of work in a lot of cases. So that's where you'll mostly see me use it, as a means of shortcutting things. All right, so back to our notes here. Okay, going into this one, we are dealing with sample spaces and tree diagrams. So in a lot of times here, we don't necessarily know all the different outcomes, so we got to kind of map them out on our own here. So let me go ahead and snip tool this. Okay, so Professor Gutierrez is making up a final exam for a course in literature. He wants the last 3 questions to be of the true-false type. To guarantee that the answers don't follow his favorite pattern, he decides, it should say, to list all possible patterns and randomly choose one of them to create his test based on. So, I'm sure at some point you wonder how teachers pick the answer key, I guess. I don't. I use programs to do it, but apparently in the old days, you had to kind of by hand choose those patterns. So, maybe this guy was just trying to determine, hey, I don't want to make it false, false, true, because that's been the last 3 quizzes, and I don't want to make anyone guessing type deal, or you don't want to spell anything out with the multiple choice. So again, that's our plausible scenario here. So for part A here, we have generate the sample space for this scenario. Okay. That's going to work. It does. Fantastic. All right, I'm going to use the pen to draw this one out. Okay, so when we think about sample space, this is all possible outcomes that we can have. So the way we're going to model this is with a tree diagram. Now, and again, and a lot of times you might be able to kind of shortcut it and guess your way through it, but when things get more complicated, a tree diagram, as annoying as they sometimes are, is our best possible thing. So it says here we have 3 questions and they're true, false. So in general, when we start off a tree diagram, we draw a dot. There's my dot, yeah? I'm going to zoom in a bit here. Okay, so each jump from a dot represents a choice or a possible set of outcomes. So when I have the first true or false question, what are the 2 possible outcomes? True or false? So choice 1, so this is representative here, this branch is going to be our question 1. And the 2 possible outcomes are true and false. That's it. Those are the only 2 possible outcomes, right? Now that's for question 1. So when I'm thinking about finishing this thing off here, what's the probability of it being true? 1 out of 2, or 0.5, right? So if it comes out to a nice decimal, you can use decimals. If it's like out of 3, then I would suggest go ahead and use the 1 out of 3 type thing. So actually, I'm just going to throw ahead and throw those out as fractions just for the sake of it. So let's say we got 1/2 over here, and then 1/2 over here. That way you're just guaranteed to get the right thing, as opposed to sometimes when you, like you do 0.33, it's not technically equal to 1/3 type deal. So again, this is saying probability of random selection. There's only 2 possible outcomes, so each one has the probability of 1/2. Now, that's represented question 1. Now I go to question 2. So this is where we get different paths. Let's say I took this path on the left here, and my first one just happened to be true. When I choose question 2, I have 2 new possible outcomes, right? So going on the true path, I yet again have 2 possible outcomes of true and false. If I chose the false path, I have 2 possible outcomes of true and false. So what these diagrams are used for is generating every possible outcome. So as I go from here, when I go to question 2, the probabilities are still the same. So since there's 2 branches coming off of this T, the chance that it's either one of these, since we're just randomly selecting, is still 1/2. Same here. I'm going off of false. The chances of either one of these occurring is still 1/2. If there were 3 branches coming off, it'd be 1/3. If there was 5 branches coming off, it'd be 1/5. So again, each thing is individual. This one just happens to be 3 true-false questions. It's not always like that. And then lastly, we have question 3, because it says we have a 3-item true-false part. So I'm going to zoom in a bit here because my handwriting's not that great with a mouse. There we go. So now off of each of these possible avenues, I yet again have 2 more branches because it's a true-false question. If I was rolling a dice, it'd have 6 branches. If I was flipping a coin, it would have 2 branches. Or my final sets of outcomes are true-false. I'd suggest whatever pattern you use when you start writing it, keep using it. Like if it was heads or tails, if you wrote tails first, keep writing it first. It just helps you kind of follow the pattern of the diagram. And our probabilities here are all going to be that 1/2. All right. So I'm going to pause this for a minute. If you haven't got that all down, go ahead and do that now. Okay, so when we look here, we have some more questions. What's the probability that all 3 items will be false? What's the probability that exactly 2 items will be true? What we want to think about here is just in general going down this and figuring things out. So the total number of outcomes is always just counting how many things occur in the last row. So if I want to figure out how many total outcomes, I'm going to look here at the last row. How many things are there in that last row? 8. 1, 2, 3, 4, 5, 6, 7, 8. So there is 8 total things that could happen. So 8 possible outcomes. So if there was rolling dice, again, you got to count a little more. But again, however many distinctive paths there are on the bottom, that's how many possible outcomes there are. So we're going to go ahead and do one way of answering these questions. So what is the probability that all 3 items will be false? We could think of the different possible outcomes. So if I go ahead and look at those, right? So if I'm following this first path here, right? So I start here, I make my first choice. I could have true, true, and true again, right? So I just followed it down the line. True, true, true. So that's one possible outcome. So I could have true, true, true. Space in there so it's actually readable. Doesn't like that. There we go. Bless you. I can go another way. So I'm going to exhaust this first path. I can go true, true, and then false. So true, true, false. So let's see. I went all the way down here. I went to this one. I went to this one. Those are done. So I can go true, false, true. True, false, true. I can go true, false, false. So again, we're just following everything down the line. So I did both of these. Now let's say, okay, so now I got to start with false. I can go false, true, true. I can go false, true, false. Then we can go false, false, true. And lastly, false, false, false. So again, depending, again, maybe some of these questions you can just intuitively figure out, but if you create the diagram, again, you're guaranteed to have everything you possibly need to answer. So we have 8 possible outcomes. Let's check. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're good there. We're figuring out probability. So what is the probability that all 3 items will be false? How many outcomes have all 3 items false? 1, right? So probability all false. There is 1 of them in 8 total outcomes. So the probability of all false is 1 out of 8. The next one is the probability that exactly 2 items are true. So when we're looking at our different things here, how many ways can exactly 2 items be true? Is this first one true, true, true? Is that qualified to exactly 2 items are true? No, right? Because that's 3. I look at my second one. Well, there's 1 way, right? So that's 1. 2, no. 3, no, no. So there's 3 possible ways. So we'd have 3 out of 8. Again, it might be a fraction, might be if it reduced, you'd have to reduce it. Probability, we could do percentages. Either way is fine. Alright, so what we're going to start with today is another example about making a tree diagram in our sample space. So for our scenario here, we have a game where first we're going to roll a dice and then flip a coin. So we're going to go ahead and work on the different parts of this example together, which I just copy and pasted over here. So we have a little bit more room to write. Alright, so when we flip this coin, alright, starting here, we are going to start with rolling a dice. So when I roll a dice, what are the possible outcomes? 1 through 6, right? So let's go ahead and draw that out. Alright, so I start with my dot. Oh, this is going to get annoying. Go away. And then I have my numbers. So 1, 2, 3, 4, 5, and 6. Yours may look slightly nicer than mine, but that's what we're going to work with here. So those are each of my possible outcomes when I roll that dice. Because again, we're just rolling a single dice, numbers 1 through 6, pretty standard dice. Unless I told you there was more than 6 sides, you can assume every dice we ever roll has 6 sides. So that represents our trial 1, or our first event of rolling that dice. And then it says we're going to flip a coin. So when I flip a coin, what are the 2 possible outcomes? Heads or tails, right? So then that second chunk here, we have our 2 possible outcomes of heads or tails. So one thing you're going to find is no matter how you actually do this, whether you did the coin first or the dice first, you have the exact same number of outcomes. It just kind of changes how the diagram looks a bit. So my advice would be when you're drawing these, start with the thing with more outcomes, just because that way it kind of makes the picture look a bit neater. All right, let's label up some of these probabilities here. So when I roll the dice, what's the chances that I roll a 1? 1 out of 6. Because there's 6 possible outcomes, and there's only a single 1. Same thing with 2, same thing with 3. We'll see today why these probabilities are useful. I know yesterday we really didn't cover that. Today we will. Now, when I flip a coin, what is the chances I get heads? 1 out of 2, right? Only 2 possible outcomes. So for each of these, we would have 1 out of 2. What's that mean? Alright, so again, if you want to go through and label all those for sake of time, I'm not going to right now. But again, all of those reds there would have a 1/2 chance. Okay, so that is our sample space here. So all of our different possible outcomes. So we want to figure out the probability of rolling a 2 and then flipping heads. So the way we can do this is by using this diagram. So we want a probability of a 2, then heads. So when we have 2 events, so this is a compound event, meaning I'm looking at 2 things, we can think about multiplying. So first idea here is we want to determine if these things are independent or not. So independent means that they have no effect on one another. When I do these 2 things, are they going to affect the outcome of one another? No, right? Assuming that when you roll that dice and flip the coin, they don't hit each other, they are considered independent. So, we have a test on this. I want you guys to do really good, okay? All right. So, when we do this, we consider them independent. So independent things and probabilities are then probabilities. So actually we can rewrite this a little bit here as 2 and heads, just so we get more used to it. So considering those 2 different events, we have a 2 and then, or you could just think of it as and heads. We can multiply those 2. So the chances that I roll the dice and get a 2 are 1 out of 6. So I have 1 out of 6 for my first probability. And then and is going to mean multiply. And we said the probability that I roll heads is 1 out of 2. So there's one way to do the problem. You can logic your way through it. When we multiply fractions, we multiply across. So I get 1 out of 12. Using the diagram to do this, it's the same kind of concept here. So if you just look at your diagram, you can follow it down. So if I was going for a 2, if I'm following this path here, so if we go down the 2 line, we see that we have a 2 here. There's a 1/6 chance for that. And then if I go down here to get heads, it's 1/2. So it's those same numbers we're multiplying. So again, the tree diagram just kind of gives you every possible outcome. And then you can multiply those probabilities there. Or you can think through them this way. Either way, we're going to get to the exact same answer. Looking at our next one, what is the probability of rolling a 3 and then flipping tails? What's the probability of rolling a 3? 1 out of 6, and tails still 1/2, right? So probability of 3 and tails is going to be the same as our first one. So we have a 1 out of 6 chance of getting a 3, 1/2 chance of getting a tails, so 1 out of 12. And again, we'd follow the diagram down, or you can just kind of go through there. So when we have independent events, meaning they have nothing to do with each other, one outcome doesn't affect the other, we can just multiply. All right, let's go ahead here and look at our last 2. So we have a probability of rolling an even number and then flipping tails. How many different even numbers are there? 3. We have the numbers 2, 4, and 6. So the probability of an even number, and what do we want? Tails. There's 3 different even numbers. So the probability that I roll it and get an even one is going to be 3 out of 6. Or if you reduce that and did 1/2, that's also fine. And the probability of getting tails is 1 out of 2. So when we multiply, reduce that, we'll have 1 out of 4, 0.25. It would be 3 out of 12, and that reduces. So 3 times 1 gives me 3, 6 times 2 gives me 12, which reduces to 1 out of 4. I'd like you to reduce it, or you could write it as a decimal. So decimal, percentage, fraction, either way works for me. But on like a multiple choice part of the test, it might be in just one of those ways. And our last one, probability of rolling a prime number. So between 1 and 6, which of these numbers are prime numbers? All right, so prime numbers. 1 is not considered prime. They are 2, 3, 5, and you got like 7, 11, 13. So it's things that are only divisible by 1 and themselves. So for some reason we don't count 1 as a prime. There's only one even prime, that's 2. That'll be useful when you guys take that placement test, remembering how to factor, fun stuff, right? All right, so how many of those exist in between 1 and 6? 3. So we're going to end up with the same probability here. There's 3 different prime numbers, so probability of a prime number. And heads, well, we had 3 out of 6 again, or just 1/2, and then we know that heads is 1/2. So we'll end up with the same thing as 1 out of 4. So again, for some of these problems, you may or may not need a tree diagram because, again, it's just going to be pretty self-explanatory on how to answer those. But yeah, useful to know how to do. All right. Looking at our next one here. Okay, so rolling 2 dice. First thing I want to talk about here is how many possible outcomes we can have. So, how many possible outcomes are there when we roll 2 dice? What do we think? So I roll 1 dice, I get 6, right? How about when I roll the other dice? It's probability for it, but the number of outcomes. We got 6 different outcomes and then 6 more. So drawing a sample space for this would be super annoying because I'm not artistic enough to make it look good. So what we're going to do here is learn another rule. When you want to figure out the total number of outcomes, you can just multiply the number of outcomes for each. So I have for the first dice is 6 outcomes. So to figure that out, we would do 6 times 6. And that works with anything. If we check back to our different things, so like yesterday when we did the true-false questions, we had 3 sets of true-false questions, right? So when we multiplied those out, I had 2 for the first question, 2 for the second question, and 2 for the third. So yesterday we had 8 possible outcomes with our true-false questions. If I was flipping a coin 3 times, same thing. I'd multiply 2 times 2 times 2. So for each event, you multiply the total number of outcomes it can have, and that gives you the total for it all. So since for each dice we have 6, we multiply 6 times 6, and we know we have 36 possible outcomes. Now, how we're going to do this problem, which is also the whole first page of your practice, which I'm going to give you the table for in here so that you don't have to figure it out yourself, is summing 2 dice when they are rolled. Basically, it's just kind of figuring out all the different sums that we can have, and then figuring out the likelihood of each. So what that's going to look like is here. Now, good question. Can you guys actually see this on the notes that I printed out for you? Yes, maybe, kind of? Okay. If you can't see it good, what you do have access to is if you go on my Twitter and into that first pinned tweet, this whole file is in there, so you can just zoom in there. There's also the answer key to the practice itself, as well as all of these videos, which is useful. But again, if not, I'll post this up at the end once we get through the notes, that way you guys can kind of write down what you need. So let's go ahead and solve a few of these probabilities together, and we'll kind of see how the complement saves us some time. So for the first one, we have what is the probability of rolling 2 dice and their sum being equal to 7. So first thing is we said we had a total of 36 possible outcomes. So I should have a lot of fractions here that involve the number 36. Now, equal to 7. So if we look at this table, how many different ways can I get 7? 6, right? So I have 1, 2, 3, 4, 5, 6. So again, if you were generating this table by yourself, you'd find out there's 6 different ways to do that. I would not expect you to memorize this table. That would be ridiculous. So again, if you guys, well, when you take the quiz tomorrow, expect this to be posted on the board. I'm more so concerned that you can solve it and work with those probabilities, not memorize every possible combination that gives you 7. But, bless you, we're just getting used to the wording here. So there's sum being equal to 7. So again, getting used to writing those statements. So we want the probability of exactly or equal to 7. And we said there's 6 different ways to do that. So the exactly to or the equal to probabilities are the easiest one. So there's 6 ways out of 36 possible ways. Getting used to reducing. So real quick here, let's do an example in GeoGebra on how to reduce. Mine's going to open. There we go. So again, 100% suggest getting a calculator, but if you don't have one, this will work as well. Let's see if I can get a keyboard here to type. Nope. Okay, so if you do not have a calculator that gets you fractions reduced and you would like to use GeoGebra to do that, what you're going to do is go to the input bar here, and you're going to use this command. It's called fraction text. And again, that's why I'm making the video, just so we can make sure we know how to do this. So fraction text, and then you put a set of parentheses. And whatever you type in here, it will simplify for you to a fraction. So in this case, we just want to check if 6 divided by 36 simplifies. And to get this fraction-y bar, I press the thing next to the shift key, where it's got the question mark, and then the forward slash, and then, or backslash, I guess. I always forget which one's which. But again, and then when you go ahead here and press enter, it reduces for you. So it just straight up, it's 1/6. So that's what reduces to. This command will also do more complicated stuff. So let's say I have a compound probability where I had like 6 divided by 36, and then I want it to get the multiply, press shift 8. And then let's say I want to do like 1 out of, or let's do 2 out of 8. Maybe I had some like weird probability that came out like that, and I want to know what it turned out to. It'll go ahead and reduce that for you as well. Oh, hold on. I pressed the wrong button. I forgot to put text. There we go. And it'll reduce it. So again, it can do pretty much all the math for you, so getting used to using that. Again, if you do not have a calculator, that'll kind of compensate for you there. Alright, so again, we know that that reduces to 1 out of 6. So just get used to reducing them. Again, when you're looking at the answer key, I think I just left everything in like its typed in form. But again, on the exam, you'd want to make sure you reduce. Our next one, probability of rolling your test and being less than or equal to 5. So we can get used to. So one thing in probability is when you're listing like a variable, you can use any letter you want. I don't care. I'm going to use X just because I'm a math teacher and that's what we're used to. So kind of putting this into an inequality here. So I want less than or equal to 5. So I want the probability that X is less than or equal to 5. Now, something you notice that throughout this course is we have to get used to inequalities and how we write them. And that's being able to rapidly know what numbers does that include. So if I want less than or equal to 5, do I include 5? Yes, because 5 is less than or equal to 5. If it just said less than 5, then we would not include. So if I want to figure this out, I want to be less than or equal to 5. We consider all the different outcomes that are less than or equal to 5. So there's no way I can roll 2 dice and get a 1, right? So I don't know why I actually included that in there. It's gone. So I'm just counting the ways that I can be less than or equal to 5. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 different ways that we can be less than or equal to 5. So for here, we have 10 out of 36, which if we reduce, let's see, we got 5 out of 18. So not a whole lot of giant, exciting conclusions thus far, but we got to get used to the wording before we can actually get into more distinctive probability. All right, for our next one, we want a sum of being greater than or equal to 6. So here, we want x greater than or equal to 6. Now, kind of the key idea here is the complement is never going to be necessary, but it's sometimes useful, right? So if I look at greater than or equal to 6, I'm including 6 in my answer. So that means I have these to count, these, and these. You can do it. It's a lot of counting, but just another example of when the complement can be useful is going to be kind of going in the other direction. So what would be the opposite or the complement of being greater than or equal to 6? So we're looking at things less than 6, right? So if I went the other way here, so the opposite of being greater than or equal to 6 is being less than or equal to 5. So if we used our complement, we could do 1 minus, let me write now, the chances that we are less than or equal to 5. And again, this is not necessary. You could just straight up count all the things that are greater than or equal to 6. But since we already did that one of being less than or equal to 5, we could do 1 minus that. So I could do 1 minus 5 out of 18. because we found the less than or equal to 5 already above, which will give me 13 out of 18. Again, or you could just count it and reduce it that way. You would get 26 things out of 36, which reduces to 5 out of 8, or 13 out of 18. So again, sometimes the complement's going to save you a little bit of time there. And last one here for the day, just getting used to the wording. So we want the sum being strictly less than 4. So here we want probability that x is less than 4. And I'm using the word strictly there just so you guys kind of get used to it. So when I'm thinking about things that are less than 4, do I include 4? No. So that means I'm just looking at 3 and 2. Oh, I don't know why it shot up to the right there. So if I'm just looking at these that are my outcomes for 3 and 2, I have 1, 2, 3 possible ways. So that'd be 3 out of 36, which reduces to 1 out of 12. So that's it for all of the dice stuff today. Again, just didn't feel like going through all these notes with you guys yesterday. I felt like that would have been pretty darn long. So what you guys can do is if you look at the first page of your practice, it's all of those dice problems. And I'm going to leave this up on the board just so you guys can reference it while you're doing that. All right, so this kind of summarizes what we already worked with last week. So probability events involving and, meaning this and this happening, or this and then this happening. So this is when we have compound events. So talking again about formalizing our word independent, which we talked about last week, is two events are independent if the occurrence or non-occurrence of one, I bet I'm trying to fix this thing, does not change the probability that the other event will occur. So again, as far as independence goes, in most cases, it's just going to be fairly informal how we define it, in the sense that we can logically say event 1 and event 2 have no effect on one another. So that's as simple as saying, like, okay, if I roll 2 dice, they don't affect each other. If I flip 2 coins, the outcome of the first thing does not change how likely the second thing is to occur. So if 2 things can or don't affect each other, then logically we could say they're independent. So that's, for example, on that quiz when we worked with true and false questions, right? So your answer to question 1 doesn't affect question 2. When you rolled a dice and flipped a coin, none of those things are dependent. Thus, to solve all those problems, we just multiplied those fractions. So probability of A and B is the probability of A times the probability of B. So when they're independent, we're just going to multiply each of those probabilities. All right, now we're going to talk a little bit about conditional probability in general multiplication. If you just write down this formula, it actually kind of covers all of the other formulas as well. So the way this is read is it's the probability. So I'm talking about this bit here. So probability of A given B. So what this means is we're finding the probability of something given something already occurred. So again, some of the examples we referenced earlier when we started these notes was the probability of passing a test given you studied, or the probability that you went to work that day given you woke up late, whatever it may be. Again, there's a bunch of those. In general, this is how we find those. So the probability of A given B is the probability of A and B divided by the probability of B. So again, we'll work with that formula a lot. The second 2 things down here are just kind of those things solved. So we talked about the multiplication rule here for when we have independent events. The other way we could do it is what's known as the general multiplication rule. So again, no need to write these because they're literally the top one just solved. So the top one is just solved there, so we multiplied probability of B over, right? But if you want to write these down, you can as well. Most times we'll just kind of walk through these and we can logic our way through the problems without having to formally memorize these rules. So if 2 events are dependent, so the go-to example of this is drawing cards from a deck. So when we start with the deck of cards, we have 52 things in there. So when I pull 1 card the first time, I have every probability. So for any given card, it's 1 out of 52. Now, if I put the card back before I pull again, those are independent events because they still have 52 in the deck, and the first card doesn't affect the second card. If I keep the first card out, so what's known as without replacement, so if I pull a card out and then I draw another one, there's 51 cards in there. Therefore, there's less things, and so it becomes dependent. Again, when we walk through those, they'll make more sense than necessarily just staring at these rules. All right. So just quick summary here. Again, not necessarily something to write down, just to kind of reference here. First step, when we're doing any type of compound probability, so A and B, B and C, whatever it may be, we need to figure out if they're independent. So if we can say that the first one does not affect the second one, we just multiply. If we cannot say that, meaning they are dependent, then we have to play with the formula a little bit here, which is more so just kind of logicking our way through those fractions. Alright, this one we're going to do one at a time, so if you just want to label these as like A, B, C, and D. The first thing up there is just the scenario, so it's giving us the what's going on type deal. Oh, wrong thing. Okay, so we're going to talk about with and without replacement. Alright, so first one, consider a collection of 6 balls that are identical except in color. There are 3 green balls, 2 blue balls, and 1 red ball. So we have a bag of marbles, right? What is the probability of drawing 2 green balls from the collection if the first ball is not replaced before the second ball is drawn? Before the second one is drawn. So if we want to write this out, we want probability, so P, of 2 green balls. So we want green and green. And again, your shorthand can be as short as you want it to. I will never grade you on writing the probability statement. I'm just encouraging you that it is incredibly useful to do so. Bless you. So I have G and G, or green and green. Now, on the first draw, I have 6 balls in the bag, and 3 of them are green. So what's the probability that I pick a green ball on the first one? 3 out of 6, or we could reduce to 1/2. Either way, I'm just going to leave it as 3 out of 6 for now. Now we have an and probability, so that means we're multiplying. Now, this is the part where the wording in these pays attention, or is very crucial, I should say. If the first ball is not replaced before the second one is drawn. So assuming I draw a green on the first one, how many green balls are left when I pick the second one? 2. How many total balls are left? 5, right? That's the trick there. So it's, again, it's not replaced. And that's the challenging part of multiple choice in this unit, is when you multiply these things out, they're going to look really, really similar. Because like they're only going to be, 0.1 apart or something. So again, making sure you pay attention to that the wording is key. So since we do not replace the second, there's only 5 balls left. So here we would have 6 out of 30, which is going to reduce to 1/5, or you could get 0.2, or you could save 20%. So again, whatever way that gets to, the key idea here is that you know what to multiply. So you know what to do 3 out of 6 times 2 out of 5. And you can answer that question in a variety of ways. So if you give me an answer, a short answer, and I want either a reduced fraction, a decimal, or a percent. You could type any one of those 3, and as long as you've done it correctly, I'm cool with it. Multiple choice, you got to go with what they give you. All right, looking at the next one. What is the probability of drawing 2 green balls from the collection if the first ball is replaced before the second one is drawn? So here we're looking at the probability of green and green again. But here it says is replaced. So when I draw that first ball, is there going to be any change from our 3 out of 6? No, right? Still talking about green. So it's still 3 out of 6. When we draw the second one here, we've put it back in. So now we've kind of reset things back to where they need to be. So what is the probability of drawing the second green ball? 3 out of 6 again. So multiplying across, 3 times 3 gives me 9 out of 36. Reducing gives me 1 out of 4. Or 0.25, or 25. That is not looking like a 1. My bad. 1 out of 4. last two examples for today. We have what is the probability of drawing a green ball from the collection and then a red ball if the first ball is not replaced before drawing the second one. So here we have probability of green and then red. So we've done this green one a couple times now, so we got 3 out of 6 for that. And it says not replaced. So when I draw the second one, how many total are left in the bag? 5. And then how many of those are red? 1. So it says 1 red ball. So that gives me 3 out of 30. Or we could reduce it to 1 out of 10. Or you can get 0.1. And the last one for the day, what is the probability of drawing a green ball from the collection and then a red ball if the first ball is replaced? So here I have probability of green and red with replacement. So we still got 3 out of 6 for our green. And then since it's replaced, this means there's still 6 balls left in there, so it's 1 out of 6. So it would give me 3 out of 36, which is going to simplify to... My bad, you guys can't see the screen right now, but I'll put it back up in a second. So we've got 3 out of 36. That reduces to 1 over 18. And I'm not going to try to approximate that in my head right now. So if we used a decimal for that, let's see if my calculator is going to show up like I want it to. I know you guys can't see, but since I'm recording this video currently, we're just going to go ahead and finish out this problem verbally, and then I'll make sure it's up there in a second. I'm literally just doing 1 divided by 18 right now as a decimal. 0.055 or 0.056 if we round. Alright, so thank you guys for correcting me after I finished the entire example on a video that is now going to be recorded. 3 over 36 actually reduces to 1 out of 12. So if we get that as a decimal, why is this not working? Alright, my computer's hating me right now. The sum up is whatever we get for 1 out of 12 is our decimal. That is what it reduces down to. So 3 over 36 reducing to 1 out of 12. Bless you. Alright, bless you again. Go ahead and open up that Excel file I sent you. Alright, so what we're going to work with today is conditional probability. So essentially what that is one of the few things we haven't covered yet. So this is using the formula that looks as follows. So we have the probability of A given B is equal to the probability of A and B divided by the probability of B. So the key ideas and ways to kind of memorize this formula is that line that's vertically written there means given. And then when we draw it out, so whatever this second thing here is, so whatever the given is, that's always the one on the bottom. The top is the and. So it's and on top, and then whatever the given or the second thing written is, that goes on the bottom. Okay, so in this scenario here, we want to look out at what we're given. So again, if anytime we see that word given, or assuming this has already occurred, any type of synonymous terms for that, the most common one will be given. That's when we want to go ahead and use this formula, see what we have, see what we can plug in. So we have in an Algebra 1 class, only 70% of the class earned a passing grade. Out of all students, 60% studied and passed. What is the probability of someone having studied given they passed? So first thing we want to do is work on writing out what it is we're finding. So as opposed to just plugging into a general formula again, I highly suggest you actually take the time to write it out, what it is you want to find, and go from there. So we want the probability, again I'm just reading the last sentence, of someone having studied, so we want the probability of studied given they passed. So this is the probability of the and. So if I look here, out of all students, 60% studied and passed. So the probability that they studied and passed. Now again, you don't want to plug percentages in. So 60% as a decimal is 0.60. So that's the probability. So again, if you take the percentage divided by 100, or just move it 2 to the left. That's how we get our probability there. And on the last thing here, so this is the bottom thing, so it's the given. So since we're given passed, the probability that they passed is 70%, so it would be 0.70. One thing to comment on the quiz, I didn't take off any points for it. If you just wrote it out how I did the answer key, I kind of tried to discuss that a bit, but you need to actually calculate it. So not just write out the work, you need to calculate the literal probability. If you just wrote the work on that, it's totally fine. I gave you credit on the quiz. I typed up the answer key as a means of you seeing what that work looks like, but you need to be able to type it in the calculator to give me either the reduced fraction or the decimal there, or again, as a percentage as well. So again, make sure on the next one and for future reference you go ahead and do that. So on this one here, we would get 0.6 divided by 0.7, 0.857. So if we go 3 decimal places is a good rule of thumb. So 0.857. So that's the probability of, given that we know they passed, there's about an 85% chance that they studied as well, which makes logical sense there as well. All right, we're going to our next one here, so more with conditional probability. So let's read the problem first, write it out, and then plug in to see what we have. So suppose that 63% of children are given a weekly allowance, and 38% of children do chores to earn that allowance. What is the probability that a child does chores given they get an allowance? So we want the probability of chores given allowance. So on the top here, we want the probability that they do both, so that they do chores and earn an allowance. What is that percentage, or what is that probability from this problem? Oh, yeah. 38%, right? It says 38% of children do household chores to earn an allowance. So that means they do both. That is the and. So it's not always going to have the word and directly in there, but again, if you can kind of infer that they're doing both things, that's how we find that. So there I have 38%, so 0.38 divided by, I want the probability of the second thing. So the probability that they get an allowance would be that 63, right? So that'd be 0.63. So 0.38 divided by 0.63. 3 decimal places gives me 0.603. One way you can tell you're definitely doing these wrong is if you ever get an answer that's bigger than 1, right? So if you're ever typing something in a calculator and it spits back something, like, so if I was here and I read this backwards, or maybe I plugged it in wrong, if I ever got something like that, I know I'm wrong, right? Because it can never be a number that's bigger than 1. So we never want something less than 0, so no negatives, and we never want anything bigger than 1. We're fighting probabilities. Last one here. In a random survey of Halloween candy bags, 80% of the bags contained orange candy, 29% contained black candy, and 37% contained both orange and black. So when these types of problems, when you're given more than just 2 pieces of information, because many of you probably looked at those last 2 slides and says, oh, you just divide. What you want to do is make sure you're plugging in the correct information. So what I would suggest right now, okay, so here, if I'm writing down the probabilities I'm giving, again, so I'm going to go ahead and translate it into words. So we have 80% of the bags contained orange. So the probability of orange is equal to 0.80. Again, there's no such thing as too much work shown in these problems. The more things you label, the more likely you are to get them right. The next sentence says 29% of the bags contained black. So the probability of black candy is equal to 0.29. And again, it's totally okay if you just write probability of B, probability of O, or if you don't write it at all. Again, some of you are going to be able to read this and be like, okay, I know where to put the numbers. That's fine. I'm just saying the more you write, the easier it is. And then the last thing, we have the probability. Let's see, 37% contained both orange and black. So the probability of orange and black is equal to 0.37. And the order in those and probabilities doesn't matter. So if I have orange and black or black and orange, they mean the same thing. So it's commutative there. We don't have a difference in those. Now, for the first problem, we need to go ahead and see here what we're solving. So we want the conditional probability. So you need to know that the conditional means the same thing as a given. So that a bag with orange candy also contains black candy. So reading that with orange candy means that's my given. I know that it has orange. So I want the probability of black candy given orange. And now if you don't read it that way and you write it the other way, you're going to get the wrong answer. Because again, you need to infer from those words that with orange implies that we know orange is in there. So once we get that out, so the top of our fraction is the and probability. So black and orange is 0.37. And then the given that it's orange, right? So that since we know that it's given, that's the bottom of our fraction. That goes on the bottom here when we divide. So we're going to go ahead and divide by that. So I'm dividing, I know the screen just went blank, by that 0.8. So 0.80. So when we divide by that, we have 0.37 divided by 0.80, or just 0.8. So 0.37 divided by 8. So if I round that to 3 decimal places, and again, that's just a good habit. If you want to do more, that's fine. So I'm going to do 463. That's our probability there. There is a typo in this one. My bad, I forgot to correct that. What's that? Yeah, 463. My bad. The typo in this is actually going to be under here. So where it says that 29% of the bags contains black candy, that should actually say 39. So let's make that into a 39 there. So my bad. So it'll just be 0.39. So as we go ahead here into our next one, so calculate the conditional probability that a bag with black candy also contains orange. So since we're saying with black, that means our given there is having black candy. And we want to know what the chances that it also has orange. So again, the and probability doesn't matter what order we do it. It's going to be the same here. So it's our 0.37. And then we're going to go ahead and divide by there the probability that has black. So as I corrected my typo there, that would be 0.39. So 0.37 divided by 0.39. So 3 decimal places, 0.949. Yeah. Again, if you can do 3 decimal places, that'd be cool. If you want to do more, that's totally fine. But in most cases, you'll see 3 gets you through pretty much every teacher's pet peeves type deal. All right, so that's all for the... All right, so we are on slide 19 here, where I'm talking about probability events involving OR. So this would be all of those like problems 32 to 39 where we could not do before. Honestly, a lot of students figured it out because they read into them, they asked questions, they got ahead and took advantage of all the time in class where they could do all of their work. For those of you that haven't, now is the formal introduction to this, so that way again you can get caught up on that and be good to go. So when we work with these types of probabilities, we can see here that we have two different types of outcomes. So the word OR stands for adding. So when we kind of try to visualize this, if we think of our Venn diagram, which you guys have likely seen before, if we look on the one on the left, so there's event A and event B. Those are two overlapping circles. When we look for the AND probability, that's the overlap. So that's where events A and B occur. If I look at the circle on the right, A or B implies all of them. So it's the overlap, just A or just B. So this is A and B. This is A or B. So what we found so far is the left side. So we've worked with that. We worked a little bit with conditionals. But we've done nothing with adding. It's always just been multiplying or dividing. So today we're going to work on finding that right side. Alright, so essentially we have two rules. The first one here, that's our general rule. So this is where we have what's known as mutually exclusive events. So you just add them together. So similar to how we kind of talked about when we did the two different AND rules, we're not going to formally write out these rules. We're just going to logic our way through these events. So mutually exclusive, by definition, means that there is no overlap. So if I think of my Venn diagram, this would be event A and event B. So there are no way they cannot occur at the same time. What this means is that the probability of A and B is equal to 0, meaning it cannot happen. So an example of this would be like if I said, what's the chances of rolling a dice and it being a 10, right? That literally can't happen. There's no 10 on the dice. So the event of rolling a dice and then getting a 10 is 0 because it does not exist. That's similar to saying what's the probability that it's both raining outside and not raining. Those things cannot happen. They're mutually exclusive. They're literally the chances that they occur at the same time is 0. So when we have events like that, we just add them together. Similarly, this is the more common rule, so this is for any events, and again, this would work as well for the other one, just because if it's equal to 0, then subtracting 0 at the end doesn't matter. But here's where, for a lot of events, we're going to utilize this rule. So the reason why we do this is to avoid double counting this part. Now, what I mean by that, if we look back at this picture, so this is A or B. So when we think about how this comes out to be, is that if I'm going to head and add up the probabilities, so A is represented by the entire circle and its overlap. So this would be A. So this is all A. So if I'm figuring out just the probability of A, it's everything in here. So it's A, and it's the part of A that overlaps with B. So if I wanted to find A or B, I'm taking that entire circle, and I'm adding it with all of B, which is represented by this entire circle. So the issue is that if we just go ahead and add every single thing together, we're always going to be double counting that middle part. So since we counted in A and B, that's where we get this rule from. So since I'm counting this portion of the circle twice, that's where that subtraction part comes from, because we're double counting that part. So to avoid, this would be like an example here, you could have a probability that's greater than 1. So that's why we created this rule here to remedy that. So in this rule is going to be the one that you'll see us use most of the time. And again, just like when we did the dependent versus independent when we multiplied, it's just a matter of thinking your way through and thinking, what would that probability be? Again, here's kind of summarizing just like the formal definition. So mutually exclusive means the probability of A and B is 0. You use that. Here, the only difference in these formulas is that this has the subtraction at the end. But if this is equal to 0, it's literally the exact same formula. So again, all we need to do is just kind of logic our way through these, just like we did with multiply. All right, let's take a look at our first example here. So we have the costless clothing store carries remainder pairs of slacks. If you buy a pair of slacks in your regular waist size without trying them on, the probability the waist will be too tight is 0.3, and the probability it'll be too loose is 0.10. So, again, advice, if you're ever confused about a problem, start writing down what it tells you. Start writing it out as probability statements. So for the first one, it tells me that the probability of too tight is equal to 0.30, or you could just write 0.3. You should know that those numbers are the same, right? The other one, too loose, is 0.1. So that's what we're given. Now, going to our part A here. So we have, are the events too tight and too loose mutually exclusive? So mutually exclusive, in other words, means that they cannot happen at the same time. So can I have a pair of pants be both too tight and too loose? No, right? That would mean that they fit, right? So those things cannot occur logically at the same time. So, and again, that's part of probability, is you have to be able to logic your way through things. I'm not going to expect, like, I'm not going to give you a problem about, like, can something be both a noble gas and, like, acidic? Like, I'm not going to throw, like, weird chemistry things in there and expect you to be able to figure them out. But if I can ask you if pants should be too tight and can they be too loose, you should be able to say that no, that cannot happen. So yes, they are mutually exclusive. So if I asked you a question like that on the test, that would be like a short answer type question. And a good response to this would be, yes, they are mutually exclusive because they cannot happen at the same time. So yes, because they can't happen at the same time. On to part B. If you choose a pair of slacks in your regular waist size at random, what is the probability that the waist size will be either too loose or too tight? So here's what we're finding. Probability of too loose or too tight. So again, it doesn't matter what order we're going to add in here. And again, you'll see I try to write the or, the and. I try to throw those in capital letters a lot just so, again, you guys can distinguish of what we're doing here. So if I want to figure this out, this is the same thing as saying probability of too tight, and or means add, so plus the probability that's too loose. Now, we said that the probability of them being both is 0 because they are mutually exclusive, but again, if you wanted to throw a -0 at the end here, that's totally fine. It's not going to hurt you. But otherwise, we can just go ahead and plug in now. We know that too tight is 0.3. and that too loose is 0.1, and thus our answer, the probability that if we put on a random pair of pants in our waist size, that they're not going to fit quite right, or that they're too tight or too loose, is 0.4. So again, the word or just means add. Not bad. I know that looked like the word 2. It should say plus 0.1. Okay, let's check out another one here. So Professor Jackson is in charge of a program to prepare people for a high school equivalency exam. That's what the GED is known as. Records show that 80% of students need work in mathematics, 70% need work in English, and 55% need work in both areas. So again, this is the example where you're given a couple of things, and if you can go ahead and plug in and solve, that's great. But again, I always suggest if you're not 100% certain, write down what you're told in the problem. So the probability that we need help in math, so I'm just going to write probability of math, is equal to 80%, so I'm just going to put it as 0.8. 0.80, again, those mean the same thing. For English, we're at 70%, so probability of English, 0.7. And then it says probability of both. So remember, the word both is synonymous for the word and. So just like when we did all those candy problems where I said that it contains both, you should know by this point that when you see the word both, that's an and probability. So here for the probability of math and English, we're told that that is 0.55. So for our part A here, our definition. Are these events mutually exclusive? Yes or no? Right, you can need help in both. So no, they're not mutually exclusive. And the reason why that is, if things are mutually exclusive, they can't happen at the same time. And we're told in the problem right here that 55% of people need help in both math and English. So they are not mutually exclusive. Even if you weren't told that, you should be able to rationalize this one that, okay, if you're taking a high school equivalency exam, chances are you might need help in both of those subjects. You may not be on par with math or English. So again, that should be something you could rationalize your way through, that those two could occur at the same time. And in the case of this problem, we're told that that probability is 0.55 and not 0. So again, variety of answers there. Big one is no, and you saying that they could occur at the same time. If they are mutually exclusive, then you would say, yes, they are, because they cannot occur at the same time. All right, so what is the probability that a student selected at random will need help in either math or English? Okay, so we said they can occur at the same time. So if I want to formally write this out, this would be the probability of math. And I see an or, so I'm going to add plus the probability of English. And then again, the last one we talked about, we could have subtracted 0. Here we're just going to go ahead and throw in that part of the formula. Minus the probability of math and English. Because again, we know that that number is not 0. The and probability is not 0. These are not mutually exclusive. So we have to subtract it at the end. So we said math was 0.8. English was 0.7. And then the and probability was 0.55. So one indicator, and again, this won't work with every single problem, but if you didn't subtract that overlap right there, if I did 0.8 plus 0.7, that's 1.5. And we know that we cannot have a probability that is greater than 1. But again, it's not like that works for every problem. This one just happens to be that way. But again, with note. So if we add those, we get 1.5. Subtracting 0.55, we get 0.95. So judging by this scenario, there's a really good shot that all these students taking the GED need help in at least one of these subjects. All right, I have 2 more slides to go. Okay, so for those of you that have been looking at that chart, that's what's known as a contingency table in the back of your packet. There's a lot of probabilities we can do with it, so we're going to do one of each today. We're going to do a conditional, an and an or probability with this. So here, we have employee type and political affiliation. This came from the textbook, so I have no idea of its validity or where it came from. I'm sure in the textbook, though, there is a citation of what business they got this from. So we have suppose an employee is selected at random from 140 Hopewell employees. Let us use the following notation to represent different events of choosing. So they just basically tell us what each of our variables is, right? So E is an executive, PW, production worker, D is Democrat, R is Republican, I is independent. So we're given this table, and the key idea here is just learning how to read it. So first thing we're going to go through is just how to read everything. So if I wanted to know the total number of executive employees, what I would do is go here, and the totals are at the ends. So if I go way over here, so there would be 48 total executive employees. So again, that's just kind of the totals. Same thing with the columns. If I want to know the total number of independents, I would just go down. From independent, go down to the very last entry. There's 17 total independents. So again, finding those totals is just as easy as that. It's just looking at the ends of the rows. And probabilities are also really easy to find on one of these tables. So if I wanted to say Democrat and a production worker, I look where those two intersect. So production worker, Democrat. So there would be 63 that are both a production worker and a Democrat. If I wanted to do executive and independent, I would take executive, go over here to independent. That's their intersection. So where they overlap, that is the and probability. the other bit of information before we get into these actual problems is where to find the total amount of people involved. Now in this one, they labeled it really nicely. They're not always going to be labeled this insanely nicely. But here, it's in the bottom right corner. So you'll notice that it's the same if you add up the rows or the columns. You always want to end up here. So this is our grand total, or this is the total amount of people involved in the questionnaire or the study or whatever it may be. All right, so let's start. We're actually going to start with this second one here because it's the easiest. So compute D and E. So we want Democrat and executive. So looking at our table, how many people are both Democratic and executive in the sample? Where do they overlap and what number is it? 5, right? So executive, Democratic, that is their intersection. So the and probability in a contingency table is the intersection. So I have 5 of those people. And then the total amount involved in the study is 140. So the probability that a randomly selected employee is both an executive and a Democrat is 5 divided by 140. So 5 divided by 140. 0.0357. So if I use 3 decimal places, that'd be 0.036. Again, if you want to use more, that's fine, but do not give answers in short answer with 2 decimal places. That's just not specific enough. I want at least 3. You can do more. Don't do like 20. That's excessive. Like 3 is acceptable. Or, like I said, you can reduce fractions, but most people prefer the decimal, so that's always easier. In my mind, easier calculation, right? All right. Let's go. So again, and probability is probably by far the easiest ones to deal with when given a contingency table. Let's go ahead and check out the or probability here. So we'll do this one next. So we have Democrat or executive. So if we think about this, if we want to write this out, so or means add. This is the probability that we're a Democrat. Or means add. So plus the probability that you are an executive. Now, if we think about this general formula, right? So we said that when we do or probabilities, we have to subtract that intersection. So this means I'm subtracting the and probability. Now, if it can occur, so if they're mutually exclusive, like we talked about in those other problems, right? If they can't be too tight and too loose, then that's just equal to 0. But when you're given a contingency table, you can just look and see what it is. So, probability of Democrat. That means I'm looking for the total number of people that were identified as Democratic. So to find the total, I'm going down to the end. That is the total number of people that identified as Democrat. So I have 68 out of 140. Because again, bottom right corner, that 140, that applies to everything. That's how many total there are. Now I want probability of executive. So if I'm going up here, total of executives, 48. So plus 48 out of 140. Now, lastly, we need to check about this probability. So probability of Democrat and executive. If I'm looking at that table, is there people that are both Democratic and executive? How many? 5, right? So we already found this probability, but not all problems are staged like that. So since there is an overlap, I need to subtract that at the end. Because as you see here, it's being counted in both the executive row and the Democrat row. So because there's an overlap, that's why we need to subtract it at the end. Now, some advice. The more you round, the more inaccurate your answer gets, and the more likely you're going to be like, why is it really close to something on the test, but not exactly right? So, unless you have a legit calculator with parentheses like a graphing calculator, here's my advice, is you need to simplify this before you plug each part in the calculator, because if you round each one, it's going to look bad at the end. So, when we add fractions, I have a common denominator. They're all already the same. So that means I'm going to do all the tops first and then divide at the end. So what I mean here, if I put all the numerators together, with some parentheses around it, then I could just divide by 140. So if I was doing this in this calculator, in order to get the right answer, I would do the top first, so 68 plus 48 minus 5. So I get 111. Then I'm going to do 111 divided by 140. So I get 0.79, and if I round it to 3 decimal places, 0.793. So again, not necessarily in need of a graphing calculator, but it would make that easy. You could just type it all at once. Either way, though. All right. And last one for today. Doing a conditional probability given one of these contingency tables. So, we're computing the probability of Democrat given executive. Okay, so the key idea here is the way we interpret the word given in here. So what we're given is that it's an executive. So again, being able to read this will drastically change how you do the problem. So this is Democrat given they're an executive, right? So what that means is since I know, or it's a given that they're an executive, is I actually only have to look at this row. So given executive means all of my decisions come from here. Now, that means the total's different. So given they're an executive, how many total executives are there? 48. So that means whatever my answer is, it's going to be divided by 48, since I know that I'm in that row. Now, looking in that row, how many of them are Democrats? 5. So given executive, what's the probability that they're Democrats? I already narrowed it down to 48 people, and only 5 of them have identified as Democrat. So the probability would be 5 divided by 48. So the answer, 0.104. We're going to do a couple more of those just briefly about what the givens, just because those are sometimes harder to understand. All right, so if we wanted to do the probability of Republican, actually, let me switch this up. So let's do the probability of production worker given Republican. So the given is what you can highlight first. Basically, you could say you know you're in that row or you're in that column because it's a given. So what this is saying is what's the probability that they're a production worker given they are Republican. So given Republican means I'm looking here, because that's where the Republican column is. So I know I'm in there. So this probability, how many total people identified as Republican? 55. So I know it's out of 55. How many of them were production workers? 21. So that probability would be 21 divided by 55. So when you're doing the conditionals, it just helps you know you're either in that single column or that single row. The other ones and or, that's when we have to use the whole table. All right, we will have one more set of notes that we'll finish up next week. But other than that, we've pretty much covered everything in this chapter so far. So you should be able to do most of the packet. The only thing I haven't technically taught you yet is the stuff about cards or permutations. So things you can't do are, it's like the second to last page. That's where we talk about this. We're not going to do that today. And then same thing here, we have not talked about cards. So if you're wanting to go ahead, you can, but just know that we will cover that next week. Okay, so just kind of summarizing what all the different things we've covered so far. Again, not necessarily something you got to memorize. We've mostly worked with thinking our way through these things. So the first one was the complement. We talked about that with dice. So, oh, not the first one. It's a third one. The first one is just the idea that if every possible outcome is examined, it sums up to 1. So that's thinking of a coin, right? So if we're flipping it and I said, what's the probability of heads or tails? That probability is 1 because that's all that can happen. Part 2 is that for any event, everything is going to be between 0 and 1. So all the answers we're giving, whether they're fraction, decimal, percentage, Again, they're represented by a probability between 0 and 1, where 0 means it can't happen, 1 means it has to happen. 3 is the complement, so just kind of reminding you of how that formula looks. So the way we wrote that was probability of not A. I forgot the A there. Is equal to 1 minus the probability of A. So that's kind of the way I've utilized that thus far. Again, not something we necessarily need, just a good way to shortcut things. Going on to 4, independent events means that basically they don't affect one another. That's the formalized rule there, but we just kind of logicked our way through that. So again, and means multiply. We've really just utilized this formula and then kind of adjusted those A's and B's as we've seen fit. Like, for example, the idea of with and without replacement. So when we change the number we're in our denominator there. So again, we haven't formally plugged into those for multiplication. But again, remembering that and, whenever we see an and probability, that's when we are multiplying. Then we worked with the conditional probability here, so probability of A given B. Again, this middle line here, we talked about that meaning given. So that's how it's read. And that's when we would do the and probability divided by the probability of the given. So whatever that second thing is, that's the probability that's going on the bottom. Getting into the last one, our addition rules, so what we covered last Thursday. A and B are mutually exclusive if probability of A and B is equal to 0. So that means if there's no overlap, right? So that's where we looked at our Venn diagrams to visualize these things of events A and B. So mutually exclusive means there was no overlap, right? This is the only version of that formula we utilized. We looked at the other one, so that's for mutually exclusive. That just means A and B is 0, so we'd lop off the last part of that formula there. But again, it's not going to affect the answer if you subtract 0. So that's all the different things we've covered for probability. That's all we're expected to know when we take this exam. So last thing we're going to talk about here before we get into examples with cards is going to be permutations versus combinations. So I tried to write this both as a formal definition as well as just a kind of a short and sweet way of understanding it. So these are two different ways of determining the number of possible outcomes. So if I ask you how many different combinations are there in a lock, how many different ways can you make a passcode on your iPhone or Android, whatever type of phone you have, that's where these come into play. So permutations. This is a formula we'll utilize whether we are trying to determine the number of possible ways in which we can assign places or put things into a given order. You'll notice that both of those things are the exact same part for each of these. So whether it's a permutation or combination, it's about assigning order, it's about putting things in place, it's about picking things, determining how many ways you can do it. So for the permutation, key idea, repetitions are not allowed, and the order in which we place things matter. So if you were to underline the distinctive characteristic there, so it matters what order we have them in. So things that are like a permutation, if I said, did you want to be the top ranked student in the class or the least or the lowest in ranking? You'd want to be the top ranked or at least higher than you are lower. So things where the order matters, if I say how many different ways can we choose president, vice president, and secretary? Bless you. Those are 3 different jobs. So if you're assigning different roles for people, then that's a permutation. So if I said how many different ways could the Chicago Marathon, how many different ways could the top 5 be played out? Well, if we had like 10,000 people participate in something, there's a lot of different ways that could happen. So events in which the order matters or that there's preference given, it's like with the lottery, if you got the great giant jackpot, right, you would have gotten more than if you got second place or third place. And the variety of ways you can get those with the lottery is like how many matching numbers you get. So again, if preference is given to who finishes, that's a permutation. A combination, repetitions are not allowed. And the, oh wait, that should be, key idea is this last part. So don't worry so much about the repetitions. We're not going to cover that as much here. It's that the order in which we place things does not matter. So again, we're not thinking about repetition here. So it's just the idea that the order in which we place things does not matter. So repetition gets into it if we're dealing with factorials, which we don't actually cover in this unit. A factorial is just like saying, like, okay, if you can keep picking the same thing over and over, then there's more combinations. But for our places, we don't have repetitions. So the key ideas we're looking at are if the order matters. So if I want to kind of adjust this here. So a permutation, the order matters. A combination, the order doesn't. So again, both deal with how many possible outcomes there are. So an example of like two different scenarios where we could look at a permutation versus a combination. If I said, again, we're picking 3 different roles. So if I said, okay, I'm going to choose 3 students. The first one gets an A in the class, the second one gets a B, and the third one gets a C. You would obviously want to be the first student chosen, right? You'd want to be the one that gets the A. Or worst case, the B. That gives preference to that. So that's a permutation because the people chosen have different things given to them, or they earn different things. Combinations would be like, okay, I'm going to pick 5 students. Every single one of them gets an A. You're all getting the same thing. The order in which I pick you doesn't matter. So again, if everyone gets the same thing, it's a combination. If they get different things, it's a permutation. All right. What we're going to do now is go ahead and go through these, and I'm going to show you as well how to type them into a calculator and how to type them into GeoGebra to actually get an answer. So, in general, the formulas look something like this. So for a combination, it's n, which is the number of people in our sample, choose r, which is how many we're picking from that sample. For a permutation, it's n pr, where n, again, n is the number of people in the sample or in the collection, and r is the number that you're picking. So the key idea here is we have to first determine how many people there are. Does the order matter in what we pick them? And then how many are we picking? The C and the P just denote which formula we're using. We'll be utilizing technology to do those calculations as opposed to doing them by hand. All right. So for our first one here, we're just going to go ahead and write out each formula, and then we're going to go and plug them in at the end. So some alternate ways you could see these formulas. It's like this. So like C parenthesis n comma r, or P parenthesis n comma r. These all mean the same thing. It just depends on what textbook you're using or what program you're using, how you're going to type them in. So this will vary a bit for each person here, depending what calculator you have or if you're using GeoGebra. So for our first one here, we have a team of 13 players needs to choose 2 players to refill the water cooler. How many possible ways can this be done? So how many total people are there in this sample? 13. So we have a 13, we know that much. And I'm just going to choose the top formatting to write this out, and then we'll talk about how to plug it in at the end. So we have 13 total people. How many of them are we choosing? 2. Now I just need to figure out the letter in the middle, right? So does it matter if I pick a person first or second, or are they doing the same thing? They're doing the same thing, right? They're both going to go refill the water cooler. It doesn't say like, oh, one person pours the water and the other has to carry the giant thing. So since they're doing the exact same thing, this is going to be a combination. So again, we'll deal with the formula determining what that means, but for now, let's just get the writing down. So it's a combination because they're doing the same thing. Right, on to the second question here. So the student body consists of 50 students. They need to elect the president, vice president, and secretary. How many possible outcomes of the election are there? So how many total are in the sample? 50. How many am I picking? 3, because we have a president, a vice president, and a secretary. So we're choosing 3. Now, are these jobs the same or different? Different. So is it a permutation or a combination? Permutation, right? So it gets a P. On our next one here, a group of 40 people are going to run a race. The top 5 finishers advance to the finals. So how many total people? 40. How many am I picking? 5. Now, does it matter what order those top 5 finish in? Or do they all get the same thing? They get the same thing, right? So there is going to be a winner and a loser, so on and so forth. But as far as the top 5 goes, they all attain the same prize. It doesn't say like, oh, first gets a medal along with this. So since they're all getting the exact same thing, that's a combination. For this one, you are setting a password. You can choose from the digits 0 through 9. You need to choose 3 digits with no repetitions. How many possible passwords can you choose from? Now, when you type a password into anything, does the order matter? Yes, right? Dog and odig are not going to both work, right? So you got to make sure that the order matters when you type in a password. If you type in your 8-digit birthday backwards into your laptop right now, it's not going to work, right? So since the order matters, we're dealing with a permutation. And then it says I have the digits 0 through 9. So how many choices would that be if I have the digits 0 through 9, 0 included? 10. So I have 10 choices. It says I'm choosing 3 of them, right? So it says choose 3 digits. So that would be 10, choose 3. Alright, let me open up GeoGebra and my calculator real quick here so I can show you how to type these things in. Alright, so starting things off here, we're going to go ahead and work with the calculator just to get a view of that, again, because that's the suggested piece of equipment that you guys would invest in by the time you go to college. So, to do that, let me adjust this a bit here so you can actually see it. Alright, so things we're going to type in here. So if you have this variation of a calculator, if you have the TI Inspire CX, like the thin one, ask me individually, I'll show you how to use it. But if you have this type of calculator, go ahead and get that out now. Alright, so to utilize these things, what you want to do here is type in this order what we're doing. So to get to it, let's say I had a permutation like one of these, right? So let's say I want to do the combination first. So it's 13, choose 2. So to figure out what this actually represents as a number, in the calculator what we would type is the number 13. So that's the first one on there, and you have to type it first. So it'd be 13. Now, to get to the command for the choose there, the combination, you click on the letter math. Or not the letter, the word math. So click on math. You would scroll over to PRB, that stands for anything related to probability. And then we're going to choose NCR. So that's where the notation comes from, how I write it. So NCR, click enter. And we want to choose 2. So I would click that. Make sure you don't press any other ones. And then press enter. So that signifies to me that there is 78 different combinations possible with that given scenario. So 13 players and choosing 2 to refill the water. There's 78 different possible outcomes there. Looking at the bottom one here. So we're looking at 10 choices for our digits 0 through 9. It's a permutation because the password, the order matters, and we want to choose 3 of them. So to put that in, I would type in 10, that's the N, right? And then same spot, so go to math, go over to PRB, and then we want to choose NPR, the permutation. So choosing 3, pressing enter. So there's 720 possible outcomes for that. You could find the other 2 problems the exact same way. So one thing you'll notice that with permutations, the numbers jump up a lot faster. The reason being is that here when the order matters, that gives you a lot of different choices. So again, if the order matters, there's always going to be more possible choices than when the order doesn't matter. So order not mattering means that 0, 1, 2 is the same as 2, 0, 1. Like so, if the order doesn't matter, it doesn't matter if ABC or CBA, it would attain the same outcome. Whereas with permutations, the order does matter. So, getting these in GeoGebra, let me go ahead and throw these in here so you can see them. I'm just showing you the actual website. So, when you're trying to look up how to do stuff on a calculator or any type of program, the internet is your friend. So I wanted to use GeoGebra and do combinations and permutations. So I typed in GeoGebra, combinations and permutations, to remind me of these commands. So here is our NPR command. So it's NPR, number, number. This one is a bit more complicated. This is how we do combinations. So I'm going to show you guys in a second how to do that. So let's go ahead and get back to GeoGebra. Alright, so we get those same numbers here. So to do the combination first, so again, if I'm someone who's going to utilize this as my technology of choice on the test, this is considered your prerequisite, your skill of showing the work. I can't tell you how to do this on an exam. So I would write down what I'm typing. You're going to type in binomial, B-I-N-O-M-I-A-L, coefficient. Once you type in the word binomial, it should pop to the top. But again, if you just start typing it, it's going to, there's really only one binomial coefficient program, or algorithm, I should say. So, binomial coefficient. And then the input's the same. So we're literally just typing in the number. So you put some parentheses. And if we want to do 13, 2, so here would be 13, 2. And you can see that we're getting that same value of 78. So go ahead and take a moment now. I'm going to pause the video so you guys can write that down if you're using GeoGebra. Alright, so that is the equivalent of the combination. So if you're trying to do NCR in GeoGebra, a little bit longer of a command, but gets us to the same goal. For the permutations, this one, we have to hit that capital P in there. So I do lowercase n, capital P, lowercase r, and then we'll see that command pops up. But again, it's just parentheses. So our one we used earlier was 10 and then a 3, so we have 10, 3. And we'll see that we're getting that same answer. So lowercase n, capital P, lowercase r, and then 10, 3. So again, GeoGebra, and I'm typing all these in that little, the input line there on the left, we get to the same spot. So regardless of what technology you're utilizing, you can get those same answers. Alright, the last set of things to consider is cards. So, things I cannot give you on the exam is a picture of the list of cards. Alright, so interpreting this picture a tad bit here, if we're looking around at it, the top row, these are known as spades. Right? They look like a pointy thing. Spear, if any of you had done gardening, that's where the term spade comes from. So it's like that elongated little thing you use to dig up like roots or to... I garden, okay? Like I accept that. All right, anyways, so that's what a spade's for, right? You garden. It's like a little hand shovel looking thing. Kind of looks like a trowel, if you know what that is. Going down to here. So these are hearts. They look like hearts. That's like, I mean, not anatomical hearts, but like the way you do them. Going to the next one, we have diamonds, and they look nothing like a diamond, but it's more of a rhombus or a parallelogram there. Going down, we have a club, which I don't know where that term came from. It looks like a clover, but again, that's what they're called. So, knowing those is useful. Going on, again, we're going to go keep flashing back to this picture. Things worthy of note. There's 52 cards in a deck. That's it. No one counts jokers. So you'll see disclaimers in like probability textbooky problems that are like, assuming a standard deck of cards shuffled randomly, those are just like typical disclaimers. Same thing if they say a classic or a standard deck, it just means that there's 52 cards and then you took out the jokers. You didn't lose any on the way to doing this problem. If we look across the rows, so if I go here, so if I look at this top row here, so all of my spades, there's 13 of them. So there's 13 of each suit. So a suit is one of those pictures. It's one of those labels. So it's a spade, it's a heart, it's a diamond, it's a club. So there's 13 of each suit. The next is our type of cards. So if I look at the first one, these are known as aces, right? The ones with the A. There's 4 of those. There's 1 ace of each suit. The same could be said of king, queen, jack. Those are the picture cards. So again, those are considered face cards or picture cards. I'm trying to hit you with like 20 years of playing cards with my grandma knowledge in 1 second here. The other ones are identified by numbers. Those are pretty self-explanatory. 10 is 10, 5 is 5, so on and so forth. So again, you have ace is the one with an A, jack, queen, king. Alright, useful facts about a deck of cards. These are things that might be useful when you're working through these problems and you're trying to picture what it is in your head. So there are 52 cards in the deck. So hint, there's going to be a boatload of fractions you're going to do that are out of 52. There are 4 different suits, so kind of like we talked about, hearts, spades, clubs, and diamonds. There are 2 colors of cards, red and black. So as we've seen here, there are red cards and there are black cards. That is it. There are no purple or blue. There are 13 of each suit, so those are the rows we talked about, so I'm just going to throw that in there if we're talking about that. There's 13 each row. There are 26 of each color, so that involves like adding them, like 13 and 13 makes 26, or you could do 13 times 2, it's the same thing. And there are 13 different values or types of cards. So I listed those out, which again you could see in the picture. So the numbers 2 through 10 inclusive, Jack, Queen, King, and then again the ace is the one with the A. Alright, so let's actually do some problems. So, for our first one, what is the probability of selecting a club from a shuffled deck? So you can see the word like shuffled deck in here. So these are the more kind of classical probability problems because they're not so basic like rolling dice over and over. So this is where you want to make sure you write out what it is you're trying to find. So taking a sentence and making it into a probability statement. So here, what is the probability of selecting a club from a shuffled deck? So that just means like they're not in like a prepackaged order. I don't know why that would ever happen, but it could, I guess. And it's a technical problem, so we're going to make sure it sounds specific. So, how many cards am I picking? 1, right? I know that because I don't see the word and, right? So, and implies you're doing a compound event. It's more than one thing. Or and then, or choosing this and then doing this, or choosing this given you did this. So those problems involve like more than one thing happening. But if we're just dealing with a straight up, like there's no and in there, that implies we're doing a simple event, so it's just one thing. So what I'm finding here is the probability of picking a club. So no and, no or, no given. So we said I'm picking 1 card. How many total cards are in a deck? 52. So it's out of 52. Now, what it's specifying to me is 1 suit. It's saying just clubs. How many of each suit are there? 13. If you simplify that, 1/4, or 0.25. Some of you who know a little more about cards may be like, okay, I'm picking a specific suit, that's 1 out of 4. You can kind of jump steps. So again, the more you know about cards, the more logic I guess there can be in these. But again, no logic needed. There's 13 of each suit, 52 total. Calculator, bam, answer. Going in the second one, same type of thing. So here it's saying, what's the probability of selecting a spade? So it doesn't matter what suit you pick. Because we're choosing a single card and just saying 1 suit, it's again, there's 13 of those, so this will be another 13 out of 52. To simplify to that, 1/4. Should be the word is, not if. My bad, typo. So here's one. What is the probability that the top card is red and a king? Now, how many cards am I looking at in this example? Alright, so if I'm picking just the top card, how many do I look at? 1. So the top card means I'm just looking at 1 card. So just saying the same idea. If I draw a card at random here. So with this card, we're looking for 1 card. So we want the probability that that 1 card is red and that it's a king. So red and king, right? So let's go ahead and take a look at our chart here. How many cards are red and a king? 2. So I have 2. And how many total cards are there? 52. Which does simplify, as someone said earlier, to 1 out of 26. Which is a decimal that it's vastly too early in the day for me to approximate. It's going to be something like 0.038-ish. Alright, we're going to add our next one here. What is the probability that the top card is black into 2? So, probability of black and 2. So the one thing we're noticing here is a lot of the and probabilities we worked with prior to cards, they were like doing 2 things. So it's like picking this marble and then doing this one. So those we'll see the words like with and without replacement. So that signifies 2 cards. So drawing this and then doing this. Here, where these top card problems, it's just trying another word of specifying to that you're drawing one item out of there. And again, the only way to get good at that language is to practice it. So we want black and a 2. How many black 2s are there? 2, right? So I'm looking at the 2s. Here's one here, and here's one here. So again, the same thing there is going to be 2 out of 52, which is going to be 1 out of 6, so on and so forth. All right, moving on here to our last 4. So we have, what is the probability of drawing a 5 and then a king with replacement? So here, how many cards am I picking up? 2, right? So it's saying drawing this card and then doing this. And then again, we got those with and without replacements. So we got to think our way through this a bit here. So we want probability of a 5 and king. Now, since we're doing 2 cards, that's a compound event. So since we have 2 different cards, so we're seeing those words of and then, those are kind of the key words here that are going to signify that we're picking out 2 cards. Because it's saying doing this and then doing this. That does not look like a D. There's that. Cards. Bless you. So then we want to figure out that with and without replacement. So if we want a 5 and a king. So if I'm looking at my 5s, right? So here are my 5s. How many of them are there? 4. So I have 4 of those. So the probability of drawing a 5 is going to be 4 out of 52. You could reduce that if you want to. You don't have to yet. And now it says with replacement. So and means multiply, right? Now I'm pulling my second card here. How many cards are going to be in the deck if I replace it? 52. How many of them are kings? 4. So we multiply. That'd be 16 out of, probably know what this one is without thinking, 2704. So it'd be 16 out of 2704, which is going to simplify, but I'll leave that up to you guys to do in your free time. Again, highly unlikely, right? So not something I'd be betting on. All right, I'm going to erase that in a moment here just so I have room to write the next one. Just going to write the answer up here. All right. There we go. Probability drawing a red and then a king without replacement. So for our next one, we're looking at the probability of red and king. So again here, we're picking out 2 cards. All right, so with that, we're good for the day. And you guys have the rest of the day as a work day.